Hello, so this is a revision video for AEP Chemistry 7.11, Introduction to Solubility Equilibria. KSP is the solubility product constant. It shows the equilibrium position of a dissolving ionic compound. It is an equilibrium constant that works in a similar way to Kc and Kp, but with a few exceptions. When an ionic salt dissolves, it breaks into its ions. For example, the solid AB solid can break apart into A+ and B- ions. They will be given the state symbol Aq to represent they are dissolved in water. When a salt is partially soluble, only a small proportion of its ions are dissolved in water at any one moment in time, meaning some but not all of its ions break away into solution. Now, the process of dissolving is reversible. As ions dissolve from the solid into solution, dissolution, some also recombine to reform the solid salt, precipitation. Because of this then, when a solid dissolves in water, some ions are constantly breaking away and entering into the solution, but also some ions from the solution are recombining to reform the solid. Eventually, the solution reaches a point where the breaking away of ions, so dissolution, equals the rate of solid formation, so precipitation. At this stage, the system is at equilibrium and the concentration of dissolved ions stays constant, even though the solid is still present. We can describe this equilibrium using the solubility product constant, KSP. It reflects how soluble a salt is. A higher KSP value means greater solubility, while a lower KSP value indicates that only a small amount of solid is dissolved at any one moment in time, so a very low solubility. To write a KSP expression for a given salt, we first must write out the reaction. So for the example just given, AB solid goes to form A+ aqueous plus B- aqueous. The KSP expression then would just simply be KSP equals concentration of A+ times concentration of B-. Because remember, we don't include solids in equilibrium expressions. For salts with multiple ions of the same type, we need to include coefficients as powers in the expression. For example, calcium fluoride CaF2 would have a KSP expression of KSP equals concentration of Ca2+ times concentration of F- squared. This is because if we look at the equation for the dissolution of calcium fluoride, we see it CaF2 goes to form Ca2+ aqueous plus 2F- aqueous. The 2F- aqueous needs to be reflected by squaring the concentration of F- in the KSP expression. Molar solubility refers to the number of moles of a substance that dissolve in 1 liter of solution to form a saturated solution. Essentially, it is a measure of how much solute can dissolve under equilibrium conditions. As we've seen, the solubility constant KSP tells us how soluble a salt is in water, but care must be taken when comparing values. If the stoichiometry for different salts are the same, we can compare KSP values directly. For example, for AgCl and NaBr, the salt that has the higher KSP value will be more soluble, because both salts just simply contain ions in a 1-to-1 ratio, so the one that has the higher KSP value is the more soluble salt. However, if the stoichiometries of two salts are different, we can't use KSP values directly to compare their solubility. Instead, we have to compare their molar solubilities. For example, for calcium fluoride CaF2 and AgCl, because the salts contain different ratios of ions, 1-to-2 in CaF2 and 1-to-1 in AgCl, the fact that CaF2 has a larger KSP value than AgCl doesn't automatically mean it's more soluble, because we haven't accounted for the fact that there are actually more ions present when 1 mole of CaF2 dissolves compared to 1 mole of AgCl. As a result, we have to calculate their molar solubilities, so the number of moles of the salt that dissolves per litre of water, before we can compare the salt's solubilities directly. Exam tip here, this is a really key rule to remember. If salts contain the same ion ratios, then you can compare their solubilities directly using KSP values. However, if the salts contain different ion ratios, then you first must calculate their molar solubilities in order to determine which one is more soluble. Common solubility rules can be explained using KSP values. For example, all salts that contain sodium, potassium, ammonium, and nitrate ions are soluble in water, and these salts correspond to very high KSP values. Equally, salts that have very low KSP values indicate low solubility, so compounds are often called insoluble in practice, even though a tiny bit of that salt will still dissolve in solution. Because it's such a small proportion of dissolved ions compared to solid, we consider them to be insoluble in the everyday world.